So everything that goes through this mic or that mic, and to a lesser degree, the ceiling mics will be heard by folks on this.
Recording in progress.
Let me open up everything. Wait. Let me open my notebook.
Okay, hi everyone. Sorry for a little bit late. So in the meantime, you can first refer to the Piazza post at 56.8 download notebooks. There will be 2 notebooks covered in this lab. So I think this lab will really focus on the first notebook. So you can try to finish that notebook in the meantime.
Would that be good?
So the mics, the ceiling mics are not great for Zoom, so make sure folks on the far end hear you. It helps to use this mic.
Okay, thank you so much.
Hello. Please, there was an announcement that was made. I did not get it. About attendance or something. I just heard you saying something, but I don't know what exactly you said.
Oh yeah. Well, I was just saying that we will just bear with us a little bit time to set up. So in the meantime, you can download the notebook from the Piazza post at 56.8. There will be 2 notebooks covered in this lab, and we will mainly focus on the first notebook. So in the meantime, you can try to finish that. Thank you.
So everyone on Zoom can hear us.
I think we can just ask them.
Hi, can everyone on Zoom hear me? Okay, cool. Sorry about the delay, but welcome to the IDL Lab 4. My name is Judy, and today I will be sharing the Lab 4 content, basically computing derivatives, as well as AutoGrad with the other IDL TA Mengchun. And the agenda will be mainly composed for 2 parts, though the first part will be talking about the slides recap a little bit, and then Mengchun will go through the notebook and we will do some exercise together to help practice. So cool, let's get started. Firstly, a really brief, simple question: what is derivative? Then we all know that a derivative is just a rate of change. So in the figure here, it's just like the slope, or we can also call it gradient. So for example, your speed meter in a car shows the derivative of the position with respect to time. And it tells you how quickly your position is changing right now. So in the same way, a derivative in a neural network will tell us how quickly the loss will change when a parameter changes. So why do we need to compute the derivatives? When we train a neural network, we know that we want to have the optimal solution for the parameters, that is the weights and the bias, so that the loss function can get smaller. And in order to do that, we need to know if we change this parameter a little bit, how will the loss change? And that sensitivity is exactly what derivative gives us. So without derivatives, we couldn't run gradient descent to optimize the model and then get the minimal loss. But here's a problem. So right now for the modern networks, there are like millions of parameters. Actually, it's like way more than that. And calculating derivatives by hand is actually impossible. So we would like to have a way to automatically help us calculate the derivatives of a function. And another thing is that for this course, we will have the autograd homeworks to earn the bonus points. So for this lab, it will also be really helpful if you want to complete the autograd homeworks and then earn the bonus points. So firstly, there are several methods that I want to share to calculate the derivatives. The first method is just use the hand coding. So basically, we use the definitions in the calculus to calculate the gradients, and we use the chain rules. And we know that for the pros, it is hand coding. So if it is well implemented, that will be very fast and accurate. But on the other side, it is also really easy to get errors, and it will cost like a lot of time to compute the gradients by hand. And the second method will be a numerical differentiation. So it means that we don't want to calculate the derivatives directly by hand, but we want to approximate the derivatives using finite differences. So for example, in the figure here, we have fx function, but instead of computing the slopes point by point, we will use some fx, like 2 points to approximate this derivative so that we can have the we can see the expression here. We will define an epsilon and then use 2 points to approximate the derivative for fx. And for the pros, it is really easy to code, but on the other side, it will be really difficult to choose epsilon, right? Because if it is too big, then definitely we'll lose accuracy. And if the epsilon is too small, it will cause the numerical error. And also, it will become very slow and error prone in high dimensions, so that it is also not an optimal solution for us. And then for the third method, we come to the auto differentiation part. And in order to know like what is auto differentiation, we firstly want to know one concept called primitive operation. So what is that? It is actually the smallest building blocks of computation in automatic differentiation. So for example, there are several different kinds of operations like addition, subtraction, multiplication, division, and we'll be covering some of the primitives in this lab. And also there are some nonlinear operations. So for example, exponential, log, sine, cosine, as well as some activation functions like ReLU, leaky ReLU, these kind of things. And we will also cover this in this lecture. And also the complex functions are composed of many primitive operations. And we want to use the nodes, that is the input of our functions, as well as the primitive operations to construct the computational graph in the forward path. And then we will call the autograd.backward to automatically help us calculate the gradients. So how does that work? So I just briefly cover it. Firstly, we'll start with the input x, and then we will use the primitive operation. For example, we have x plus a, x multiplied by a, these kind of primitive operations to incrementally create the computational graph. And then we will automatically track the computations from backward. So we will starting from the last node, and then we will pass the gradient node by node based on the topological order in the computational graph. And then we will continuously update the parameters during this gradient calculation. And also, when we are implementing auto differentiation, there's like a really powerful tool called PyTorch auto differentiate engine. Then we can simply call this autograd function, and then you can calculate the gradients automatically. So for this auto differentiation method, the pros will be the backward is automatically calculated as long as you have the computational graph constructed correctly during the forward path. But then on the other side, the cons will be you should be really careful when you want to implement this forward function, because if you have the node implemented incorrectly, then in the backward function, the path, the gradients will not be the gradients in the backward path will not be passed smoothly. And let's take an example to see how automatic differentiation works. So for example, here we have this f equals to b multiply a plus b, and we want to know that how a and b affects f. So we will be looking at the gradient of f with regards to a and f with regards to b. And we all know that for the answer here, for f, the gradient of f with regards to a, because it is like only a here, so it is b for the final results. And for f, the gradient of f with regards to b, it is b plus b, that is a plus 2b. And how is it calculated? So firstly, in the forward pass, let's make a computational graph. And for this expression, firstly, we have two nodes. One node is input A, the other node is input B. And then we have a primitive operation here, that is the plus. And in order to, for convenience, we will just call the temporary result here C. And after we get the result of C, we'll then multiply B by C and finally get the function f. So this is the other primitive operation here, the multiplication. And then we start with the final node. So here, that is the f. And we know that the gradient of itself is simply 1. So here we know that the gradient of f with regards to itself, it is 1. And then we use the chain rule to calculate the gradient in the backward path. And then after we calculate the gradient of f, we will go to C and B in the reverse topological order. And here we know that because f equals to b multiplied by c, so the gradient of f with regards to c will be using the chain rule. That will be f gradient with regards to f multiplied by f's gradient with regards to c, and it will be 1 multiplied by b. So simply here we get the results of f's gradient with regards to c will be b. And the same thing for b here. For this path, we know that if we want to calculate the gradient of f with regards to b, then it will be 1 multiplied by c, so this will be c here. But for when we and after we calculate the gradient of f, we will move to the node c, and then we will have we can see like there are two paths here. So one is the gradient of c with regards to a, and another will be the gradient of c with regards to b. And we can use the same way, the chain rule, to calculate the gradient here. So for example, here, for the gradient of f with regards to a, we can use this. Firstly, we calculate the f's gradient with regards to c, and then we multiply by the c's gradient with regard to a, and it will be 1 multiplied by b multiplied by 1. So it will be b here. And then here, there will be two paths for node B to contribute to the gradient of f here. So one is the path of C to B, and one is the path of f to B. So here we will have the two gradients add together. One is f with regards to B, and one is the f's gradient with regards to C multiplied by the gradient of C with regards to B. And finally, we'll get this B plus C result. So any questions here? Okay, cool. Then let's go ahead. And yeah, and this is basically how we calculate the gradient in the backward pass. So if we want to implement this method using our code, then we need to first initialize the node class. And inside the node class, we know that firstly, we will construct the computational graph. And in the computational graph for the forward pass, we'll have some nodes, for example, node A and node B. And these nodes will contain some data. For example, A equals to 1, B equals to 2, and we need each node to contain the data, and we need some data structure to store these data. And here, the small tip will be we can use a NumPy array to hold the data with each node. And also, we know that in the backward propagation, each node will be computing the gradient for like f with regards to a, for example. So for each node, we need to also hold its gradient during the back propagation. So it will be also a NumPy array of the same shape as the size of the data. But here, because we are accumulating the gradients, so we will first initialize all the nodes in the gradient array to be 0 for an initialization. And then finally, we also need to keep track of the parents of the node, because in the backward propagation, we will pass the gradient through the pass. So we need to track what is the parent node of each node. So for example, here for node C, the parent will be A and B. And because we want to only calculate the gradient once when we do the back propagation, so here we use the set data structure to store the parent nodes, just because we don't want to duplicate. And this is a way to implement the node class. So just as what I have said before, so for the initialization function, inside we have the data as in NumPy array with the size of the data itself. And then we will also store the gradient. And for the gradient, it will be array with all zeros for the initializations. And finally, we will have a set for the parent nodes. Okay, so now let's stop here, and then Mengchen will walk us through some exercises in the notebook.
Thanks so much for Judy's clear overview on the derivative computation. Now let's work on the notebook. So first thing you need to download the notebooks is at the Piazza post at 56.8. And there will be 2 notebooks. You need to download them and upload to your drive, or just save a copy to your drive. Then let's start. So let's first start with the first cell, block cell. This is about basic node class, which is just introduced to you before. So we want you to, based on your understanding from these previous slides, try to complete it by yourself. We will give you like 2 minutes, and we will go through the answer later. Okay, let's work through this answer. So you can also refer to the slides on the right. You can just see this computation graph as a simple autograd framework. So you can see that for every input and the operation, there are the node. For example, the A, B are the input node, and the as operation gives C, the multiplication gives F. So for each node, we need to track three things. And this is also the three things that we need to initialize in this node class. So first, we need to check the self.data. It's the value of your node. For example, the value of A, B, C, or F. And it's usually stored as NumPy array because it's very easy for you to handle. And then we need to check the grad. This is the gradient for the backpropagation. We use np.0slide to initialize it to zeros and also make it as the same dimension as your data. And when we do the step backward, we will add all the contributions to the grad. For example, you can see on the right for B, it directly contributes to F, but it also goes through C. So we will add both parts as a B.grad. And then the last thing we need to check is the self.parents. The underscore is not necessary. It's just a convention to indicate that this variable is private. So let's get back to this parents. It means the parents node. The parent node means the node that creates the current node. For example, you can see in this graph, C comes from A and B. So A and B is the parent nodes for C. But for A and B, they are only the input node, so they do not have parent node. Okay, that's all for the first cell. And then it comes from our first checking. We also have the pose in the Piazza pose on lab 4. It's not strictly, we will not grade you based on this poll, but we recommended you to participate so that we can track your progress on the notebook. And also, if you have any feedback, you can just leave them under the post. Then let's get back to the slides. Judy will then introduce you with many various of primitive operations that you are used in the autograd.
I think there's a question on Zoom.
Yeah.
Oh,
Can you see it?
wait, I don't have Zoom.
Yes, let me check. Okay, I see the questions on Zoom that you ask why we do not use that. For this self.parents, I think it depends on you. You can use set or you can use list. It's fine. Okay, let's move to the next part.
Yeah, because basically for the set data structure in Python that we can avoid the duplication, but it's also fine if you use list as a data structure to store all the parent nodes for the current node. It's also fine. Okay, cool. So now we finished the exercise of constructing the node class. And what we also need for constructing the forward pass in the computational graph, we know that we also need the primitive operations, right? So for the primitive operations, we know that there are examples of addition, multiplication, matrix multiplication, that is the matmul, subtraction, as well as some nonlinear function like log, exponential, these kind of things. And we will walk through it one by one to see how we implement these primitive operations. So firstly, this is the addition. It's a really simple expression, C equals to A plus B. Then how to compute this primitive operation? So let's firstly assume that for the gradient of C, let's just call it gradient of C. And then means that when we, for the addition node, for here, when we want to calculate the gradient of C with regard to A, we know that it's 1, right? And we also using the we are also using the chain rule, so it will be the gradient of C multiplied by 1. And same thing for the gradient of C with regards to B. So using the chain rule, it will be the gradient of C multiplied by 1. So what does this mean? It means that when we back propagate through an addition node, the gradient from the output will be simply passed back unchanged to both inputs. So the addition is one of the simplest primitives. That's in backward. It just distributes the incoming gradient to each parent. And now let's see how we can implement this addition primitive function. So firstly, we create a new output node. And this output node will represent the result of adding two inputs, so that we know that we have one node of A, we have one node of B, and then in the node class, we store the data of A and the data of B, and then we need to compute them, and then add the data from the input nodes. And then we will record the parents of this node. So the graph will know that the result will come from A and B. And then we will define a backward function. And in back propagation, the function will take this incoming gradient and then pass it unchanged to both A and B, because the derivative of addition with respect to each input is just 1, right? We just mentioned that. And finally, we will set this backward function on the output node. So when AutoGrad calls dot backward function, it knows exactly how to propagate the gradients through the addition. So this is the code implementation. As we just see previously, firstly, we'll have this add node as the addition primitive. And then for this function, we have two inputs. One is the A node, and the type is the node class we just implement. And another one is the B node. And firstly, we'll create this out node. So the type is also a node class. And inside of the node class, we'll initialize it. So firstly, we will add the two nodes data together. So this will be A node dot data plus B node dot data. That is the value of the out node. And then we will keep track of the parents of the node. So we know that we use A and B to calculate this. So here we have the A node and B node as the parents nodes inside this set. And then we will define the backward function. So we know that because the gradient of addition is just simply 1. So here for the A node's gradient, we will just simply add the output's gradient. So for example, here it is just the gradient with regard to C, and then same thing for B. We also just add it for the gradient of C. And finally, we will call this backward function and return the result. So this is the primitive addition function. Is there any question? Okay, cool. And now let's move on to multiplication. So for multiplication here, for example, C equals to A multiplied by B, we know that when we want to compute the C's gradient with regard to A, we'll use the chain rule again. So it's C's gradient with regard to C multiplied by C's gradient with regards to A. So it will be C's gradient multiplied by B, and that is the same thing for B. It will be the C's gradient multiplied by A. So for the implementation of multiplication primitives, it's the same thing. We create the new output node, and then we multiply the data from the two input nodes, and then we keep track of the parents in the set, and then we define the backward function. And in this backward function, we add the gradient of the multiplication gradients from the node, and finally, we will set the node's backward function to track it. So this is the code implementation. We have the node initialized, we have the data to be multiplied, and then we track the parent node. And in the backward function, for A's gradient, we will multiply by B's data, and for B's gradient, we will add the gradient for the output gradient multiplied by the A's node data, so just as the expression here. And finally, we call this backward function and then return the output. So this is multiplication. And we all know that in neural network, it is more complicated than that. We will use matrix multiplication. So here it is just the mat mode. And in NumPy, we will use this at for the mat mode in the NumPy function. And also, if you want to calculate the inner product, it will be using this function called NumPy dot. And here, for C equals to A matmol B, when we calculate the gradient with regards to A, it will be C's gradient multiplied B transpose. And for here, for C's gradient with regards to B, it will be A transpose multiplied by C's gradient. So it's the same thing. And this is the code implementation. So here we, instead of using add or multiply, we have this add as the matmol, and then we have the parent node for node A and node B. And then in the backward function, we add the gradient. So here we use numpy dot dot to calculate the gradient for matmol. And then for A's gradient, we multiply by the output gradient multiplied by B transpose. And so for B's gradient, we multiply by A transpose, same thing. Okay, cool. So this is basically how we compute the forward path. And then how does the backward work? So let's go back to this example. So for example, here we have the expression of B multiplied by A plus B. Then what do we need in the backward propagation? We need three things. So first one is the backward list. So why we need this backward list? It is just a queue or a list that stores the node in the order that we will process them. Why do we need that? Because we need to make sure that we always compute the gradient of the output node first, and then we will move backward to the inputs. So in other words, the list will enforce a topological order for backpropagation. And secondly, we need to track the parent node of the current node. So each node needs to know which input nodes it came from. This is because during backpropagation, the gradients must be sent back to those parent nodes. So without this information, the algorithm wouldn't know where to deliver the gradients. And also we need to keep track of the current node. So here, when we do the initialization, we have the backward list as empty, and then we have parents and current nodes to be initialized as none. And then we will go from the final node. So for example, here, that is the F, and then we will put it in the backward list. And we know that the parents will be C and B because there are two paths that contributes to F directly. And we know that the current node is F. And then we go back to one node. So now the current node is C, and we put it to the backward list. And we know that for C, the parent node are A and B. And here we then go back to the node B for the current node, and then we put B in the backward list. And we know that because B is the first node, so B doesn't have any parents, so that we set the parents to be none. And the same thing for A. Finally, it is in parallel with B. We have A to be added in the backward list, and it doesn't have the parents, and the current node is A. So this is how the backward function works. So after we have this backward list, we will then just iterate through the whole list. And this is how backward works. So for the pseudocode, we will first initialize the current node gradient to an array. And why do we have it initialized as all ones in the array? This is because we first start from the final node F here, and we know that the gradient of F with regards to itself is just 1. So we will just initialize all the gradients in the array to be 1. And then we'll initialize the backward list as an empty list. And then just as I mentioned before in the example, we'll recursively take node in the topological order. And first we need to check if the node is already in the backward list. So if it is, then we don't want to duplicate the computation, then we will just skip. And then we will iterate through the node's parents and then recursively build this backward list until the recursion stops. And finally, after we get this whole backward list, we'll iterate through all the nodes in the list. And then if the node has its parents, we will call the node.backward function to automatically calculate all the gradients. So this is just the code implementation for the backward function. So inside the node class, we have a function called backward, and then we initialize the backward list as empty. And then we will initialize the gradient as an array with all ones, and the shape or the size of this array will be the same as the input, so it will be self.data size. And then we will build a recursive function called build backward list here. And then we will take a node as the input. We first check whether it is in the backward list. And if it is not, then we will append this node, add it to the backward list. And then we will recursively call this function to all of its parents. And finally, we'll call this build backward list to build the list. And finally, after we get it, we will iterate every node in this backward list coming from like F, C, A, B in this topological order. And then if the node has parents, we will just call it the backward function to calculate gradients. So that is how the backward function works. Oh, okay. So I think there's also like another note. So that is when you are working on the AutoGrad homework, when you want to manually create new nodes, we need to be very careful. So first, we must not use the raw data of the input nodes directly. So for example, if we have a node with its data stored in like a.data, we must write the new node, maybe like node a.data multiplied by 2, then it means that this new node will not be connected to A in the computational graph because they will break the AutoGrad and the gradients cannot flow back through this path. So if you want to create a new node and for example, you want to multiply 2 by this node, then you cannot simply use this a.data multiplied by 2. And instead, you need to create a node called 2 and initialize it as using the node class that we implement. So for example, 2 equals to node 2, and then we will have this new node called using the primitive operation multiply. So it will be new node multiply A and 2. Okay, let me see if I can be more clear using the chalk. So it's just when you want to create, can you see it? So it's just when you want to create a new node. So for example, you want to have A multiplied by 2 in your computational graph. And the wrong way to write it is new node equal to node A dot data multiplied by 2.
Would you like to put that screen up for a moment?
Okay, let me see how I can do that. Actually, it's just really quick. So we cannot do it as 2 here because when we are constructing the computational graph, we will want to use the function path, right? And then we will pass the gradient on the backward function. But here, if we simply use 2 here, then we don't know, the computational graph will not know like, what 2 is. And instead, if we want to do this thing, then we need to first initialize the node maybe called 2, and then use this node class that we just implement. So for example, like here, the data for this node is 2, and then we use this node class to implement a new node, and then we will have this new node equals to node a dot data multiplied by 2. So only by using this way, the computational graph can know that which nodes we are using, and then we can track its parents' nodes, and finally we can pass the gradients in the backward function. And yeah, I think that's it for my part right now, and we can do some exercise with regards to the primitive operations.
You want the screens back down?
Oh yeah.
Thank you.
Okay, let's work on the primitive operation first. So let's first try to complete the add operation and also the mul operation. So remember, whenever you just finish one block, remember to run this test so that you know if you implement them correctly. Let's do it for 5 minutes and we will get back. Okay, everyone, let's go through the primitive operation together. So let's first go through the add operation. So in this function, it takes in the A node and B node as the input, and at 0, we will do the element-wise addition, A plus B. So within this function, we first create an out node that we just call the node class that we have implemented before. And we feed the inNode.data plus bNode.data as a data, self.data. And also we pass this tuple to check the parents node, that is A node, B node. And then for the backward, we define this add backward function. So within this function, we will update the gradient. And one thing to note that is that we at here, we will use plus equal, not just equal. So why we do that is because if you just record the graph in our previous slides, you can see that for example, for B, it will have so many paths to contribute to its gradient. So in this case, we do not want to overwrite or just only keep the only paths of the gradient update. So we want to add all of them. So that's why we use plus equal. And then after we finish this function, we will just set this function to attach the function to out. So whenever we call the backward function on out, it will run this add backward function and know how to push back the gradient backward to the parent nodes. Then we will return our out. Okay, let's go through the mole operation. It's basically the same idea. So at 0, we will do the element-wise multiplication, A multiply B. It will also take in A node and B node. And also, we will create the node, the out node that we call the node class. And we pass the A node.data, multiply B node.data, because we do the multiplication at here, right? And then we will check the parents node. Sorry. After that, we define the mole backward function. Also, we update the gradient as there. But the one thing is very different from the add operation is add here. So for the addition operation, the derivative with respect to the input will only be 1. But in the multiplication part, it will depend on the other input. So that's why we multiply the other input. For example, if we take the derivative with respect to A, we will just treat the B as constant, and vice versa. After that, we also attach this backward function to the out, and then we return the out. So in this out, it will have its self.data, the parents, and also know how to push back the gradient to the parents nodes. Okay, here is a checking 2. To save the time, we will skip the matrix multiplication. And let's first try to implement this backward method. We will give you 5 minutes, and let's do it now. Okay, everyone, let's go through this answer for the backward method. So we first we call the class nodes that we have implemented before. It's just that we add a new method that is a backward function. So within this function, we will first initialize the backward list and also the self.grad. To simplify the question, we just initialize it to a bunch of ones and with the same shape of the self.data. Then we use this function to build the backward list. So it works in a recursive way. For every node that is not in the backward list, we will append the node to the list. And then we will move back to the parent node of this current node and also call this build backward list function again. So again, if the parent node is not in the backward list, we will also append this parent node. So in this way, we will go through all this. Any questions? Okay. So in this way, we will build the backward list that is starting as a current node and move back through all of the parent node. Then at here, we just call this build backward list to set up this list. Then we will iterate every node in this backward list. So you can see this command. If the node in the backward list and if the parent node of this node exists, we will call the backward function. Otherwise, we will just add it to the input node. So the general idea of this backward method is that first we will use the recursive way to build the backward list, so that the list will starting with the current node and moving and we will moving through all of the parent node. Then we will iterate through all the nodes in this backward list and call the backward function to just push back the gradient to the parent nodes. Okay, here is the checking 3. Any questions? Okay, let's move on. So let's get back to the slides. Judy will give you some introduction on some activation function. It's not really hard, but it will be a little bit tricky when you try to implement them by yourself in the homework.
Okay, so I will go through several nonlinear activation functions. So for example, here for soft plus, this function is you first have 1 plus e to the power of x, and then we put it for the log e. And this is how the activation function looks like in the graph. And there's only a tiny thing that you need to pay attention to. So here, because we have 1, here, but we cannot just create a scalar for this one. And instead, we need to initialize a numpy array of all the ones using this numpy.ones like array because we want to match the shape of this one array with the shape of x. And we will also provide you with the exponential and the log n primitives implementation, so you don't need to worry about this. So here it is just the implementation of the soft plus node. So firstly, we have this exponential node, and then we will have this add node to add the two, like here, 1 plus e to the power of x. And just need to pay attention to, like here, we use this numpy.ones like to initialize the array of ones, and the shape will be the same as x.data. And then we take the log node primitive operation to get the log output, and then finally return the out node. So for the leaky ReLU, the tricky thing here is we have like 2 different parts for the expressions. So we have like x is more than 0 or x is smaller than 0, and it corresponds to like different expressions. So here, if we can just look at the code. When like x is more than 0, we want to use this numpy.where to choose this second operation for 1. And on the other hand, if x is smaller than 0, then we will choose 0 here using the numpy.where. So we will use the positive and negative, like 2 nodes to initialize the different nodes when x is more than 0 and x is smaller than 0. And also we will have this alpha mask node. So this is the similar to the one that I just talked about in soft plus. So here we want to use this numpy.ones like to initialize the array with all ones, and the shape will be the same with the input.data. And then we will calculate the positive and the negative part by using the multiplication primitive. So that is input multiplied by the positive mask node and the input multiplied by the alpha mask node, which is the negative part, alpha x. And finally, we'll add them together, and that is the leaky ReLU implementation. And finally, we come to the tangent edged function. So for the tangent edged function, it is a little bit tricky because we have 2 parts, the denominator and the numerator. And actually, we want to compute them separately. So we all know that in both denominator and numerator, we have both e to the power of x and e to the power of minus x. But we don't want to reuse the exact same node for both. So we all know that here we have e to the power of x, but we don't want to only initialize one node for e to the power of x and use it in both numerator and denominator. And this is because when we using the same node, then it might cause an issue during the backpropagation. Because in our framework, the gradients for the intermediate nodes are updated only through one path at a time. So if the same node is shared across numerator and the denominator, then the one of the gradient updates will get lost or even overwritten. So here, instead, what we want to do is that we want to build separate nodes for each occurrence, even if they look the same. So for example, here for the numerator, we will have one exponential x1 And then we will have another node called exponential x2 for the denominator, and also the same thing for e to the power of minus x. So we will have like one negative x1 in the denominator and one negative x2 in the numerator. And in this way, each part of its graph will have its own copy, and then the gradient can flow correctly through both branches. So here the main takeaway is just when implementing the tangent h in function, don't try to be clever by reusing the same e to the power of x node. And instead, we want to build it twice for each side, and then the autograd can handle the gradients properly. So here is the implementation. It just, here we can see that we have like two exponential to the power of x. We have one for the denominator and one for the numerator. And the same thing for the e to the power of minus x. And then we use these primitive operations, for example, add, divide, and multiplication to calculate this tangent h activation function for this tangent h primitive operation. And that's basically it. And then Mengchen will talk about the nonlinear activation function implementation, and then we will go through the PyTorch autograd engine for a little bit. Thank you.
Okay, everyone, we do not have enough time to let you implement every cell. So if you want, you can just open these answers, the solution for the part 1 notebook, and we can go through all the activation function together. So just give me a second. Let me just open this. Okay, let's start with the first activation function, soft plus. So if you go through this formula, you will see that it's just a natural log of 1 plus e to the x. You do not need to take the derivative by yourself. The backward rules that already embedded in the primitive operations can handle that. So the general idea for us to implement the activation function is that you try to use a primitive operation to construct this graph. And there's some place that you need to note. So for this one, as mentioned before, you cannot just construct a scalar single one. You have to create a constant node and use and initialize it as a one with the same shape as e to the x, so that e can plus to the one can plus e to the x, and then you use and then we also provide the natural log node and also the exponent node for you to implement, so that you can just construct this graph. Okay, if we go through the code, so here we define the log node and also the exponent node, the primitive operation node for you. And then within this function, you first apply this exponent node on x to get e to the x here. And then you create a constant one matrix that's with the same dimension as x data, so that you get 1. And also use add node to combine those. So you combine 1 plus e to the x, and you get here. Then finally, you just apply the log node to the e plus e to the x, and you get the final results. So here is the checking for. Any question with this function? Okay, cool. Let's go through the leaky ReLU function. Okay, for leaky ReLU function, it will be a little tricky because you can see on the right, it has the condition branch. So how can we just construct this computation graph? So you can see that for x greater than 0, it will be x itself. But if the x is smaller or equal to 0, it will be alpha multiply x. So here, the alpha is a similar way as we dealt in the last activation function. So we need to create a node with a matrix of alpha and have the same shape with x. And how can we handle this conditional branch? So one idea is that we will create the mask node for it. So we first create a positive mask node to handle this positive branch. And then we will construct a -1 to handle the other branch. So if we go through this code, we can see that we first create the alpha node as we implemented before. And then we try to create the positive mask node. That is, we use np.where to handle this condition setting. So if the data is greater or equal to 0, it will get 1. Otherwise, it will get 0. And here we use dot point. This point is that we want it to be the float type, and we do not want it to be the integer. And we use a similar way, we will get the negative mask node. After that, we just multiply the alpha with the negative mask node, because if x less or equal to 0, it will multiply by alpha. Then we get this positive part and negative part. After that, we use this add node to combine those parts, the positive one and the negative one. So then we get the leaky ReLU function. Do anyone follow here? Any questions? Okay, let's move on to the next. The tanh function. This will be the most complex function that we will ask you to implement by yourself. And it also appears in your homework. So we want you to get a sense and a little bit intuition on that. So again, let's work through this formula. If you see this formula, you can see that e to the x just shown twice. So one is in the numerator and one is in the denominator. And it's also the same case for e to the minus x. So when you see this formula, you may have some intuition that you want to separate this function into two parts. One is in the numerator part and one is in the denominator part. But the issue is that if you use a shared node, for example, you use the shared e to the x in these two paths, since each node only calls a backward function once, so that means if you handle this function in two paths, at last, this node will only get one gradient update, and the other gradient update will be lost. So we do not want that. We want to add this gradient. So one way to handle these problems is that we may consider to copy the shared node. For example, we can set e to the x1 and e to the x2 as two copies of e to the x. And also we can set e to the minus x1 and e to the minus x2 as two copies of e to the minus x, so that we can just separate this function into two paths. One is numerator and one is denominator, so that for each path, the backward can flow in correctly, and they can also be added back into the x.grad. So let's go through this code. This is a derivative node and also the exponent node that we have defined for you. Then let's go through this node. So it's the same way that we create a neg1 node, and then we just use small node to multiply neg1 and x to get the minus x. Then we apply the exponent node to the x to get e to the x. Here, this one. And then we use a similar way to get e to the minus x. And also we just multiply -1 to get minus e to the minus x, this part in the numerator. After that, we just add this node so that we get the numerator calculation at here. And then we use a similar way to get the denominator calculation. So at last, we will just combine the numerator and denominator. And we use this derivative node to handle that. Just combine the numerator and the denominator. Then we get this function. Okay, here is the checking 6. Any question with this function?
Then why do you need to create the exponent again? Why can't we just use the one created for the denominator, just use it for nominate?
For the denominator part?
Yeah, why do we need to create lag input 2 again? Can't we just use the lag exp up there?
So, okay. So we first need to create the minus x. Do you understand that? We use more nodes.
I don't want to know why can't you use the lag x like that you created for numerator. What's the issue? What's the issue with reusing it? Will that create a problem for backward?
For Edward?
I mean, why can't we not use the lag exp that we created up for the numerator?
In the numerator part, right?
Yeah, the exp x and lag exp lag x already created. Why can't we just use the exp x for the denominator as well? Is that because this will create a problem for the backward function?
Yes.
Actually, I just talk a little bit about it for like the tips you can see in the slides here. It is because if we want to use the same node, for example, for like exponential x, then when it is shared across the numerator and denominator, and when we do the backward pass, one of the gradient updates will get lost or overwritten. Because for the nodes in the computational graph, if we don't have separate nodes for denominator and numerator, then there's only like one node, then we'll have like two paths, so that when we are updating the gradient, like on one path, the value will be overwritten. So the solution to this will be we have denominator and a numerator calculated separately here, and then we have like two copies. So exponential in the denominator and exponential in the numerator. And otherwise, it will cause an issue for overwritten the gradients when we reuse the same node in both denominator and numerator. Does this sound good to you?
Yes, thank you.
Okay, no worries.
Okay, then let's just quickly move on to the part 2 notebook. Okay, I will just give you a quick go through of this notebook. So for the part 2 notebook, it's that we just give you a simpler framework for the homework 1P1 autograd framework. It's not just as same as the autograd 1, but just give you some ideas and let you have some sense of what's going on in this notebook. So in the autograd 1, we need to build autograd and implement operation backward function, and also build some models that is similar that you have used in the homework 1P1, the linear activation and also the loss function. And then here is the operation class. In this class, we will record all the operations that we've done. For example, we will track the input, output, gradients, and also the backward operation. And then here is a gradient buffer. So while you can just see it as a memory storage of all of the gradients. So why do you need this? It's because in the future, you may need to handle many of the gradients. So it's better for you to have a class to save all of this stuff. So in this gradient buffer, let's say you have the add sport function so that you can init the sport to hold the gradient. And then you can update the gradient by call this function update parameter. After that, you can retrieve them, use get parameter function. And then we have the autograd class. So in this class, this is a forward pass, the add operations. In this function, you can just implement all that we have implemented in this lab 4. For example, some primitive operations like add or multiplication. And then here is a backward. So in this backward, you can also implement like as backward or exponent backward, something like that. And after that, here is a linear class. So the linear class, it is essentially it's a combination of matrix multiplication and addition, because it's like x multiplied w and plus the bias. So this part that is the only part that you need to implement in the part 2 notebook. Just a small hint is that you may consider how to combine the addition part and the multiplication, the math-more operation to finish this part. Okay, that's all for today's learning. Thanks for listening and have a good day.
Thanks for coming.